Hello guys, this is Hao. So today I decided to record a video to just retaught like what is a Jacobian matrix, because I think yesterday I used an example that is just way too hard for you guys to understand. Another day I figured out actually there's a much simpler way to teach it. So I want you to reteach it, and hope you guys could spend like 10 minutes to just watch this video clip, and hope you guys can understand what we were doing or what the lab is want you guys to do yesterday. So all the goal of yesterday's lab is trying to analyze the stability of an equilibrium point. But to reach that point, we need to talk about what is stability for a system first. So here, let's just focus on the continuous time system. So the continuous time system, it's different from what we have learned as a discrete time system. So in the matrix form, the left-hand side for discrete time is the next state, while in continuous time, it's the prime, the changing with respect to the current state. So that's the difference. And this difference makes them have totally different characteristic. So before we jump to that, I'll first talk about what is stable, or what would make the continuous time system stable. I think the class that I already showed you guys is, if we have the equation that is x dot equal to ax, or is it x prime equal to ax, well, a and x are just scalars, or one-dimensional. A is a constant. X is just one variable, state variable. And x at time 0 is x0. Then we can say that the time function of this x is x0 multiplied exponential at. If you wonder like why this is the answer, you can just take derivative with respect to this x and replace it to put on the left-hand side. You figure out if you replace x with these value here, this equation will stand. And also, if you let t to 0, exponential 0 is 1, so it's also equal to x0. So the above condition will all be fit if you make x equal to that. And this idea could be expanded into a matrix way, or to multiple variables. So if you today you don't have just one variable, you have actually two, and they will affect your derivative values, which is actually what I show here. X dot equal to a11 multiply x plus a12 multiply y, and y dot equal to a21 multiply x and a22 multiply y. But all these a here are just constant. So if this condition or this relationships exist, we call it a linear continuous time system. Since the derivatives of any state variables are just constants multiplied, or constant combinations of the current state. And the solution of that is similar to this result here. So if you just need to write it in the matrix way, which is you put the initial condition as a vector, put it at the end of the result, and the front multiply exponential a is this matrix multiplied t time. You say, oh wait, could the power of exponential be a matrix? The answer is yes, but it's not covered in class. So if you are wondering what it looks like, you can come to office hour and ask me. But all I can tell you here is this exponential at, it will become a function, or sorry, a matrix. And inside that matrix, every term, these all the terms inside will just be a function of t. It's a function, a matrix multiply a vector, become like a vector. So that's become a vector, which is actually what we are looking for, the xt. The capital X of t is a vector, which is this xt and yt. So that's the answer we're looking for. But this is not the main point for today. The main point today is, so if we say we want to make sure these x or x and y's will not go wild, they will somehow converge to one equilibrium point. What is the criterion? And the criterion is here. So let's first talk about scalar case. If we have the equation that is x dot equal to ax, then in order to make sure this x, after how long the time is, it will just go to one equilibrium point and stay there. That a value has to be less than 0. The example is here. Suppose a is less 1,000. When time goes on, that t become a large number. The x, this function, will become x0 still constant. We don't know initial condition, but multiply exponentials of something negative really huge. Exponential of something negative really huge is really close to 0. So 0 multiply anything will still be close to 0. So that means this x at least goes to converge to the equilibrium point 0. So that's for scalar case. But what about matrix form? If the system looks like this, how can I say the system is like stable, or the x and y will go to one equilibrium point and stays there? The result is this matrix A. If we want to make it stable, we need to have an eigenvalues real part less than 0. So for now, you can just remember this conclusion. If you can write a system, x dot y dot equal to some constant matrix, multiply the current state, x and y. This is a linear system. If you want to say this x, if this x and y just goes to a stable, constant value, equilibrium point and stays there, then all the eigenvalues of this matrix need to have negative real part. That's the first conclusion. However, this type of system, we call it a linear system. X dot equal to current x and y multiply some constant. It's not a common case or general case. Most of the equation we have seen here, like x dot x prime equal to, like we say logarithm of x, or like x multiply y stuff, right? These equations are nonlinear, so we know. So if it's nonlinear, how can we tell if this value goes to equilibrium point, or that equilibrium point becomes saddle point or unstable equilibrium? How can we determine that? You may say, okay, let's just find the eigenvalues of like this, what we do here, right? Like here, you can just find the eigenvalue of the matrix, and then see the eigenvalue of the real part is less than 0, then stable, non-stable. But that's not possible, because you see here, this equation here is the vector to a vector, so it's not a matrix. Vector does not have eigenvalues. So what can we do? Can we still find the eigenvalues of it? So the answer is yes, but no. Yes is, yes, we can find some eigenvalue, but no is, it's not the real eigenvalue of that, because this, of course, it's not matrix. It won't even have the eigenvalue. But we can find some way to approximate it. So here is this. So to analyze the stabilities, we always want to make the system look like a linear system, like this. Constant multiply these x and y's equal to x dot and y dot, or x prime, y prime. However, we only have, this is all we have, which means it's not matrix. So we want to make it a matrix. So how to do that? The process we do here is, we call it linearization, or the verb is linearize. So okay, what does that mean? All right, so let's just view in this way. Suppose you have 2 points, x1, y1, x2, y2. You know, x1 dot equals to this function here, right? Just need to put the x and y as the x or what current x, y you have. Here I use the first point. And here, sorry, a typo here. This should be y dot, y1 dot, sorry, not x2. Let me change it. Alright, I'm back. So here I just changed this, so that was a typo, so it should be y1 dot. So we know for this 2 point, at this the first point, x1, y1, I know the x1 dot equals to g of x1, y1 dot equals to h of x1, y1. Like, just basically follow this relationships here. So what is the x2, y2 dot? The prime, sorry. So just remember, all the primes are equal to the dot I use here. I prefer dot because it's easy to type. Could just think of the dots are just primes, all right? Okay, so what is this? They're primes here. You can say, oh, simple, right? It's just followed by this equation. So I just put g of x2, y2, or y2 dot, just h of x2, y2. That is simple, right? However, this is not what we're looking for. Because you can, since g and h are just two functions, and this does not fit the form we want to see here. We want to see this form. Some constant, not a function. We want a constant and multiply the current state, which is I want to see x1 dot equal to something multiply x1 plus something multiply y1, and x2 dot is something multiply x2 plus something multiply y2. And this function form is just not something we want to see. And so the result here is, if it's not linear, we can actually approximate it, make it close to zero. So the approximation formula is this. You can say, well, although we could do x2, y2 directly input into the g function and get x2 dot. However, we can actually use some information from the x1 dot. We only use info from here to construct x2 dot based on all the things we have in x1 and y1. How to do that? The result is if you just take partial of that thing, the whole g, to x and multiply the difference of this x2 and x1, plus you just take partial of the whole g function to y and multiply the difference in y. So this is like the tangent line of this g with respect to x, and then you find a tangent line of the g with respect to y and multiply the difference. This is like linear approximations, and plus the current value we have. Then this whole thing will be close to the x2 dot, this value we want to find. However, it's not the same. It's just close, but not the same. So it's an approximation. To differentiate them, I put a hat here, a triangle. I call it x2 hat dot. Quite complicated. Hope you guys can get used to it. This is a really common way when you describe approximations. If you are studying in university, I mean, in your senior year, I believe it will be quite common if you keep working on math. So following by the same rule, you can get the y2 hat dot will be also the same thing as you take partial of these h with respect to x first, multiply difference in x, plus you take partial of that with respect to y, multiply difference in y, and plus the current h. So this is a linear approximation. You only use x1, y1's value here, right? This is all related to x1. Maybe a little bit of x2, but this is like only appears here. The rest are just x1s. So when we say we only use x1 values information, it actually means anything that relates to g and h only takes input from x, y, and y1 from this point. And by this info, we can retrieve the x2 dot and y2 dot here. Now you may ask, say, so how? What's the benefit? Why want to do that? Because this could help us analyze the equilibrium point. Say, wait, how do you do that? So let's just try. So if you make, let's just first now, okay, from here, we assume x1 and y1 are the equilibrium point. So at the equilibrium point, what we know, g of x1, y1 is 0, right? H of x1, y1 is 0. So if you just put this condition back to here, what we get? The same thing, right? But these guys are 0. So become 0, remove them. And now we get this. x2 dot equal to that plus this, multiply this, right? This is what we get. Okay, how? So you may say, okay, how? So what's that help the benefits it? Okay, so now so this here looks like what we're looking for, right? Quite close. Because x2 dot equal to something. This partial g, partial x at x1, y1 is a constant. Because we already know what the x1, y1 point is. By the way, x2 could be any point as long as nearby x1, okay? So now it looks like we have some constant multiply x2, right? x2 dot equal to some constant multiply x2. And some constant multiply y2. However, there's still some redundant thing, x1 and y1. Although it is a known value, but still annoying. It's still not the linear function form, linear system form we're looking for. So now the question is, how can we, take a further step to make it into this form? The answer is, we could actually change the coordinate to a new coordinate. Let's just define a new variable called m. The m, which is equal to x2 subtract x1. Okay, so here we replace one thing is we only use x2 as a state variable. x1 is an equilibrium point. So as an equilibrium point, it's a known point. It's a fixed value. So x1 and y1 are just value that's fixed. So which means a partial of this x1, y1 also just a constant fixed value. So now the m equal to like something x2 subtract x1, right? And equal to m2 subtract y1, y2 subtract y1, and what x1, y1 are just constant. So say why you do that? Patience. So if we do that, okay, then the x2 hat subtract x1 hat is just the m hat, right? And since x1 hat, we say x1 is just the constant, so there's no changing. So it becomes just the hat is just 0. So it's 0, and also for the y's, but since they are just 0, so adding them or removing them doesn't really make any difference. So just put it here. They are 0 because they are equilibrium points. They won't really change, and also because they're just constant here. Maybe I should just replace the equilibrium point comment. Just say, because x1 and y1 are just constant, so they won't change. If time derivative of that is just 0. So if that replacement, I hope you guys are fine with that. If you can accept this replacement, then you can see it's all thing here. It's just x2 dot subtract x1 dot, or sorry, x2 hat dot subtract x1 hat dot, and equal to some constant multiply x2 subtract x1 plus some constant multiply y2 subtract y1. And all these stuff, if you just replace all these x2 subtract x1, y2 subtract y1 with m and n, will result here. This. Now, this is a much favorable form we want to see. We have one variable m, but if dot equal to some constant multiply m, and some constant multiply another variable n. And so does the n dot. This now is a pretty nice linear system. And if you change it back to a matrix form, you get this. And this, what does this tells us? So can you guys still remember? So if you test the eigenvalue of this matrix, we call this matrix called Jacobian. So if we take it has the eigenvalue of the Jacobian matrix. If we say the eigenvalue of this Jacobian matrix is less than 0, the real part is less than 0. In the previous statement here, we say if the eigenvalue is less than 0, all the x and y's will just goes to 0. So if this Jacobian matrix eigenvalue is real part is less than 0, all the m and n will just goes to 0. Then what does m and n goes to 0 mean? M equals to x1 subtract x1. x1 is a fixed constant. It's an equilibrium point. x2 will be just like any point nearby it. If that is true, then that means if this is 0, that just means x2 equals to x1, which means it goes back. Any point nearby it will eventually goes back to that x1. Or you say any x value nearby it goes back to x1, any y value nearby it goes back to y1. Or you can say any point nearby the x1, y1 point will goes back to it, which makes it a stable equilibrium point. So this is why we say analyzing the Jacobian matrix eigenvalue could tell you whether this point is stable equilibrium point or not. Because just based on we make this, that we actually, so if on the other word is we will make the difference of any point with respect to the equilibrium point as a new variable. And by that, we can build a system of their difference. And if we see that all the difference will eventually converge to 0, which means they all goes back if the eigenvalue is less than 0. If the real part is larger than 0, well, it'll just go away. So which means it's a non-stable equilibrium point. So here is a simple table I make to talk about, so what's the effect of the eigenvalues? The real part affect whether it's stable or unstable. Stable or unstable. If it's 0, that means they won't change. I mean, align with equilibrium, or just rotate, have a center and rotate around it. An imaginary part determines how fast that the trajectory spiral. If it's 0, then there will be no spiral. And there's an example here. So the example is, if I have these two functions, x prime and y prime, they equal to that. Okay, and you can plot the vector field. Based on the vector field, you can see this point stable or unstable. You can see it's unstable. Every point trying to move it away from it. So by looking at this function, we can directly tell there's one equilibrium point that's 0 and 0, right? 0, 0, which is here, center. This is one equilibrium point. From the first graph, we know this is an unstable equilibrium point. So now we know it's unstable, but does this result fit with our approximation by the Jacobian? So now I just calculate Jacobian here. So I got Jacobian. And I approximate it. Sorry, my bad. So if you get a Jacobian, and since the equilibrium point is just 0, 0, you get 0, 3, 3, 6. And the eigenvalue of this matrix, by putting x and y's are zeros, I think is one positive, one negative. So things that have a positive eigenvalue, it is non-stable. So that's why this equilibrium point is non-stable. However, this Jacobian method, testing an eigenvalue Jacobian method, only valid at a point nearby that equilibrium point. If it's away from it, it will be different. The way to see that is if you just plot the vector field, okay, it looks like that. But if you plot the vector field by the Jacobian, you say, wait, how to do that? Oh, that's simple. Because Jacobian, on one hand, is actually means this, right? The changing of G and changing of H by multiplying the difference of X and Y. Or I should look back to here, right? Changing of that equal to the change, something multiply change of X, something multiply change of Y plus original. And if you do that, you put it, so now you can calculate the other nearby points, say the prime, based on that approximation. If you do that, So you get a Jacobian. You calculate the Jacobian at that equilibrium point, which is what I do here. And then you plot the vector field by using that Jacobian's value, multiply the difference of the x and the difference of the y plus the prime value at that point. You can also plot the vector field. But this time, this vector field is only similar at the value that nearby that equilibrium point, which is actually here. So if you compare these two vector field plots, they're actually different when they are getting away from the equilibrium point. They are similar when nearby the equilibrium point, but they are similar here, but different. You see, different here at the corners. They are totally different. So which means this approximation method is only valid at the point nearby the equilibrium point. And that is why the lab asks you guys to plot two vector fields. One is original vector field, so here, and one is the vector field that is approximated by the Jacobian. They want to tell you that the difference, it looks different. That is, I mean, away from the equilibrium point, but similar at nearby the equilibrium point. All right, I think that's all for today. I hope you guys could understand more about the meaning of Jacobian and what a linear approximation is.